AP Calculus BC, Unit 4 review, corrective to get you ready for the retest. So this will be some good practice. So the first problems, I'm just trying to convert to exact Cartesian coordinates. So this is r and this is theta, and I would say probably one set of formulas you should have memorized is x equals r cosine theta and y equals r sine theta. Now this all comes from the basic idea of polar coordinates being related to x and y coordinates. There's a radius, there's a theta. So what happens is you get a right triangle, and this is the same as x. The length of this is going to be over the x coordinate. The length of this is going to be the y coordinate. And so if you're set up trig, you can say, well, if I want to get y from theta and r, that would be sine. Sine of theta equals opposite over hypotenuse. And cosine of theta gives you adjacent over hypotenuse. And from those, we get our basic formulas for converting from polar to Cartesian. So, I mean, we use them a lot, so you probably start to memorize them, but if it's been a while, just go back to the basic idea of what polar is. So in this case right here, it's going to be 12 cosine 4 pi over 3. So reference angle is pi over 3. Pi over 3. So for both of these, it's going to be in quadrant 3. So cosine is negative, and it's going to be 1/2. So we get negative 6 for your x coordinate. And sine in quadrant 3 is negative, root 3 over 2 at that reference angle. And so we get negative 6 root 3 for the y value. And so your final coordinates, negative 6 comma negative 6 root 3. There we go. Now we can go the other way, convert to exact polar. So we're going from xy to r theta. So some of the other basic relationships that come from this is x squared plus y squared equals r squared. So 1 squared plus negative root 3 squared equals r squared. So 1 plus 3 equals r squared. 4 equals r squared. Square root of both sides, plus or minus. Algebraically is two answers, but the radius is always positive. To get the angle theta from x and y, you'd use tangent of theta equals opposite over adjacent, y over x. So that's going to be root 3 over 1. Now I'm going to try and figure out what angle that happens at. I'm going to think of these as over 2 because I want to think of them as sine over cosine. And so the reference angle is, one is sine root 3 over 2, one is cosine 1/2. That's pi over 3. What quadrants could we be in? Well, one's going to be positive, one's going to be negative. So this would be quadrant 2 and quadrant 4. And if you got to decide which one it is. Now, based off this, what quadrant are you in? If you're to the right one, down root 3, it's got to be quadrant 4, right? So, sure, there's infinite answers here, but we're going with quadrant 4 based off what the Cartesian coordinates are. And so theta equals 5 pi over 3. So your coordinates are r first, theta second. There you go. Find the equivalent polar coordinates. So It's trying to find another one that has the same thing. Now, a drawing picture could be helpful. 4 pi over 3 is over here, right? 4 pi over 3. And it has radius of 6. Now, this one has a negative 6 radius. That means we got to get over here so that it gets flipped backwards. So we could take away pi, and that would leave you at pi over 3. We could add pi to this and be 7 pi over 3. I mean, there's a bunch of possibilities, but this would probably be the most immediate one. This one here, negative 2 pi over 3, would be right there. And negative 4 would be over here. So this is where the actual coordinates end up putting us at. So to get to the same place with the positive radius, we could just go. We could add pi to this, and that would be, you had pi over 3. You could add another pi, that put you at well, you'd have to add another 2 pi at that point. Or you could take pi away from that and be negative 5 pi over 3. So negative 5 pi over 3 would put you all the way over here, right? I mean, this is probably the better one. So I don't know. Find a picture helpful with those. Find the center and radius of this circle. So this is one of our polar shapes. And whenever it's sine or cosine with just a number in front, then that's going to be a circle of one-petaled flower. This is your diameter. I mean, you could always make a little table. And circles will repeat themselves twice. So you really only need those values. So if you plug 0 in, cosine 0 is 1, so you get negative k. Cosine pi over 2 is 0, so you get 0. Cosine of pi is negative 1, so you get positive k. So if you were to graph this, this would be negative k. That'd be your first point on it, and pi over 2. So I mean, this is 0's pointing to the right, but it's negative, so it goes left. Pi over 2 is pointed up, has a radius of 0. And then once you get back to pi, it's positive, so it's 0 again. So this is the circle here. So the center is at negative k over 2. Find the center and the radius. So the radius is k over 2. And the center in Cartesian coordinates is negative k over 2, comma 0. In polar coordinates, that would be, I mean, there's different ways to do it. You could say angles, you could say a radius of negative k over 2 and a angle of 0, which is coincidentally the same. Do positive radius, k over 2, and then you have to put pi in there. That's Cartesian. This is polar. All right, polar sketches, constant angle, all radii, right? Well, that's just going to be constant angle pi over 6. So I usually, I don't know, try and sketch pi over 3. And pi over 6 would be halfway. So it's going to be this line. It's going to be all the dots that have the same angle with every possible radius. It's going to be a line. This one right here is going to have a constant radius for all angles. not constant radius. We're going to put all angles in. The radius is going to gradually get larger. So for 0, you're going to be at 0. At pi over 2, you're going to, we can make a quick little table. So it's going to be 0, negative pi, pi is going to be negative 2 pi, negative 3 pi, negative 4 pi. So at pi over 2, you're facing up, but has a negative radius down to 3.14. And then pi, you're facing to the left, but has a negative radius of 2 pi. So it's going to be over here. I guess I could have made my graph a little smaller. It's going to look like this. It's going to be like a spiral. Archimedes spiral. Okay. And we're only doing 0 to 2 pi. So otherwise you'd get another one on the other side too. Okay, cosine of 3 theta. This is a rose curve. And it's going to have 3 petals because it's an odd number inside. Second set of petals ends up, there are 6 petals, but the second set ends up on top of the first. So we're actually going to go through the shape twice. The radius is the number in front, which is 1. And I think it would be good to find the tips of the petals. I'm going to sketch the picture. I'm going to try and make use of all this room, which will make it easier. So I'm going to sketch a circle, and I'm going to make that 1. The bigger you make these, I think the easier it is to make them look nice. So the tips are going to be when the radius equals plus or minus its maximum radius, which is 1. And so you say, okay, well, when does cosine equal 1? Well, that's at 0 plus pi k, because we're also including negative 1. So theta equals 0 plus pi over 3k. So theta equals 0, pi over 3, 2 pi over 3, pi, 4 pi over 3, 5 pi over 3, and 2 pi. Remember, the second set of petals ends up right on top of the first, so you could just do the first one. So 0, this is going to be the tip, pi over 3. Try and divide this into 3 equal places. So this is pi over 3. Now, remember, well, the first one is going to be positive. The second one at pi over 3 is going to end up being negative down here. And then 2 pi over 3 is going to be positive again. So it's going to be there. And then pi is going to be over here, but it's going to be negative. You're going to be back here. You're going to be done. So when you plug in, so we're starting here at 0. So it's going to end, this is the second one. So this is the first petal. This is the second petal. This is the third petal. So it's going to go like this. It should look like it's coming in towards, you know what we should do? We should split the angles in between the tips, because that gives you the asymptotes of the edges of the petals. So it should look like it's coming in like an asymptote or a tangent right here to this, and then it goes nicely into the next one. And the tops are very smooth. So I need those other angles in there for your flowers to look good. And then it finishes the first one at the end. So the direction is, it starts right here and it goes like this, right? So this is the initial and terminal. Point, which is at 0, 1 in polar. Oh, sorry, 1, 0 in polar. Also 1, 0 in Cartesian. Okay, so that's what I'm looking for. Number of petals, nice graph. Okay, this next one is another rose curve, but it has 4 petals because it has an even number inside. So the second set of petals ends up actually staggered from the first set. The radius is 1. So I'm going to go ahead, excuse me, and sketch a circle that it fits in, which I really need. If yours is, if you don't do this and then I do it and your petals look like they're not big, long enough or too long, I'm going to take off points. We want to figure out what the tips are. And so that's going to be when r equals 0. And so sine equals 0 at 0. Oh, wait. Sorry. When r equals plus or minus 1. So that's going to be when 2 theta equals pi over 2 plus pi k. And theta equals pi over 4 plus pi over 2k. And so theta equals pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. So we're going to sketch those angles. Pi over 4 is just like a 45-degree angle. Cuts the quadrant exactly in half. And then the other angles are already kind of on there, so that's nice. The first one, sine starts at pi over 4. You get a positive. Just imagine the sine curve. The sine curve looks like this, right? So that first peak you hit is positive. If there was a negative in front, then the first petal would be back here. So this is your first petal. And then at 3 pi over 4, it should go to negative. So this is the second petal. And then 5 pi over 4 should be positive again. So this is the third petal. And then 7 pi over 4 should be negative again. This is the fourth petal. So we're starting, if you plug 0 in, you get 0. So we're starting here, and this line right here should be a tangent to your rose petal. So it comes in like that. Goes nicely in. And it looks more like a, like a clover, full leaf clover. So it starts here, and the direction is like this. Okay, so the initial and terminal points are at an angle of 0, radius of 0, or same with Cartesian, that's origin. Okay, number 9. Now, whenever you have the section number added, this is going to be some kind of like limacon. So I usually just make a table to help me out. But when these numbers are the same, it's going to be a cardioid. So that should help you. Kind of heart-looking shape. Make a quick table. Just to, and then whenever it's sine, it's vertical, cosine, it's horizontal. So it kind of helps you. But other than that, I don't try and remember much about these. Sine of 0 is 0, so you get 2. Sine of pi over 2 is 1, so you get 0. Sine of pi is 0, so you get 2. Sine of 3 pi over 2 is negative 1, so you get 4. And sine of 2 pi is 0, so you get 2. So we're going to need to go all the way out to 4 at some point. So I guess we're going to just go ahead and make our, and I forgot to, in the last one, add the units on the axes because I scaled it differently. This time I think we go all the way to 4 because we actually do need 4. So 0, 2, angle 0, facing right, radius of 2. Pi over 2 is 0. Pi 2 and 3 pi over 2, 4 is going to be down here. And we'll be back there. So these should look very roundish. Okay, not pointy. Even if in my solutions I have something that looks like that, they should come out like this. Okay. So it starts here, goes like that. So this is the initial and terminal. It's a radius of 2, angle of 0. All right, this one is probably going to be some other kind of limacon. I mean, cardioids are limacons, but these numbers right here aren't the same. I'd make a table and just put some values real quick. Should be vertical sort of in orientation because it has sine on it. Sine 0, this is going to be -2. It's going to be -1, -2, -3, -2. So I think I'll just go with leaving the axes the way they are. Okay, so 0, -2. 0 is to the right, but it's negative, so it's over here. So this is the first spot. Pi over 2 is up, but it's negative, so it's down. So that's the next one. 3 pi over 2 is, sorry, pi is to the left, radius of 2. 3 pi over 2 is down, but it has a radius of -3, so it's up here. So it's not, it doesn't have an inner loop. That's what this would, this would end up in here if it had an inner loop. So it's, and it doesn't have a cusp either. So this is like, call it like a convex limacon. It kind of goes out like this, or flattened. You know, it's like a circle. It's been like pushed in a little bit on one side. Okay. Let's go to the next page. All right, polar derivatives. I would draw a sketch of these because it gives you a lot of information that can help you know how many answers you can get, where they should be, and if there's any weird things like is it horizontal or vertical at the same point? Can't be. Which one is it? It would take L'Hopital's rule to algebraically prove it. I'll go ahead and let you support it with a graph. So this is a cardioid, right? So let's see if we can squeeze a table in here. I'll do it over here. Theta r, 0, pi over 2, pi, 3 pi over 2, 2 pi. So 0, 2, pi over 2, 0, 2, -4, 2. So the graph is, let's see. It is right. Okay, hold on. 2, 0, 2. Oh, this would be positive 4. So it's bigger underneath. It's cardioid, so you might just give yourself a little more room. So 1, 2, 3, 4, 1, 2, 1, 2. 0, 2, pi over 2, 0, pi 2, 3 pi 2, 4, and we're back there. So this is what the graph looks like. And we're going to look for horizontal and vertical. So we should get a horizontal somewhere around here, horizontal somewhere around here, horizontal around here, vertical around here, vertical here, and vertical here. Now this cusp is probably going to come up as a horizontal in our work. So now we know what to expect. So now horizontal tangents, that would be when dy dx equals 0, which means that dy d theta on the top is 0. Vertical is going to be when dy dx is undefined, which is going to come from the denominator being 0, dx d theta equals 0. Because remember, dy dx equals dy d theta over dx d theta. So see if we can do the work for this. I'd write down what x is. X is our cosine theta, which is going to be 2 minus 2 sine theta cosine theta. And y equals our sine theta, which is going to be 2 minus 2 sine theta sine theta. I'd probably just leave that. I probably wouldn't multiply those out. So on part A, we're looking for dy d theta. And so that's going to involve a product rule. So it's going to be 2 minus 2 sine theta times the derivative of sine is cosine theta plus sine theta times this derivative is going to be negative 2 cosine theta. And we're looking for it to equal 0. So we're going to set it equal to 0. And we're going to solve. I'm going to go ahead and distribute this. So I get 2 cosine theta minus 2 sine theta cosine theta minus 2 sine theta cosine theta. I'm trying to write small here. We combine like terms. 2 cosine theta minus 4 sine theta cosine theta equals 0. I'm going to factor, and usually factoring is what you want to use on these. Sometimes you got to use some trig identities, but I think this one's going to work. 1 minus 2 sine theta. And so then we have cosine theta equals 0. Sine theta equals positive 1/2. Reference angle, pi over 6, quadrants 1 and 2. This is going to be theta equals pi over 2 plus pi k. This is going to be theta equals pi over 6 plus 2 pi k. And theta equals 5 pi over 6 plus 2 pi k. So theta equals pi over 2, 3 pi over 2, and we're just looking from 0 to 2 pi, and pi over 6, and 5 pi over 6. Now, we expected for horizontals to have 1, 2, 3 of them, and at pi over 2, that one should not be horizontal. You could prove it with L'Hopital's rule, but from the picture, it's vertical. And don't say because it's a cusp. Cusp doesn't rule out a horizontal. You can have a horizontal on a cusp. You can just say it has a vertical tangent there. You could say since graph, you could just say since graph is vertical and have a picture of it, show me a vertical written on it, and I'll believe you. Otherwise, you got to do L'Hopital's rule to defend your answer. Now, b dx d theta is going to be 2 minus 2 sine theta, derivative of cosine's negative sine, plus cosine theta times negative 2 cosine theta equals 0. So let's distribute this. Negative 2 sine theta plus 2 sine squared theta minus 2 cosine squared theta equals 0. So this is where we're going to have to use a trig identity to get everything in terms, because right now if you try and factor it, it's not going to work. There's no GCF. So I think we want to get everything in terms of sine, because we have a sine to the first sine squared here. So cosine squared is 1 minus sine squared, right? Pythagorean identity, sine squared, sine squared plus cosine squared equals 1, right? So that means cosine squared equals 1 minus sine squared. And a bunch of other identities come from this. So we're going to have negative 2 sine theta plus 2 sine squared theta minus 2 plus 2 sine squared theta. And we probably want to put this in sort of like a standard form, treat it like a polynomial, quadratic trinomial. 4 sine squared theta minus 2 sine theta minus 2. You can factor the 2 out. And we could factor 2 sine theta and sine theta. And you gotta have ones here. One's gonna be positive, one's gonna be negative. To get negative here, you want this one to be negative. Right? Negative 2 sine theta plus 1 sine theta gives you negative 1 sine theta in the middle. So sine theta equals negative 1/2. And sine theta equals 1. Alpha equals pi over 6. Quadrants 3 and 4. So theta equals 7 pi over 6 plus 2 pi k. And theta equals 11 pi over 6 plus 2 pi k. And theta equals 3 pi over 2 plus 2 pi k. So our answers are pi over 2, 7 pi over 6, 11 pi over 6. And our picture tells us that there are 3. 1, 2, 3. This is where we would have an issue that came up in the last one, but this is vertical, okay, because of the graph. So there you go. That's how you do it. You could do L'Hopital's rule. I believe I have the work for that on my solutions that I'm not going to do right now. Okay. Okay, 12. Find the equation of the tangent lines at the pole. So there's a shortcut here. I mean, first we could say x equals r cosine theta equals 1 plus 2 cosine 2 theta cosine theta, and y equals r sine theta 1 plus 2 cosine theta 2 theta sine theta. Now to find this is how you're going to find your coordinates, by the way. But you got to find the angles first. So you got to figure out, well, when is the radius 0? So that's got to be one of your first things to do. When is the radius 0? So yeah, okay, well, it's going to be cosine 2 theta equals negative 1/2. So alpha equals pi over 3, quadrants 2 and 3. So 2 theta equals quadrant 2 would be 2 pi over 3 plus 2 pi k. And 2 theta equals 4 pi over 3 plus 2 pi k. Theta equals pi over 3 plus pi k. And theta equals 2 pi over 3 plus pi k. And so we're looking at pi over 3, 4 pi over 3, 2 pi over 3, and 5 pi over 3. So those are all the angles that this happens at. And you don't need to find the xy coordinates because you know that they're 0, 0 because we're at the pole, right? So x and y are 0. You can plug these in, but that should confirm that. Because the radius is 0, which would make x and y 0. Now to find the slope, the slope we wrote up here is dy dx over d equals dy d theta over dx d theta. So you could do all that work, but there is a shortcut at the pole because the radius is 0. Like half the terms drop out, and there's a shortcut. Now, if you don't remember the shortcut, then don't use it. But it's going to be tangent theta at the pole, only at the pole. So I'm going to use that, which saves me a fair amount of work. So then we're going to do pi over 3. So that's going to be sine of pi over 3 over cosine of pi over 3. And so sine of pi over 3 is root 3 over 2 over 1/2. Gives you root 3. So that's that slope. dy dx at 2 pi over 3. It's going to be sine of 2 pi over 3 over cosine of 2 pi over 3. Reference angle is pi over 3, so we're going to get root 3 over 2 and 1/2, but the cosine is going to be negative. All right, we'll do the next one. So we're getting root 3 over 2 and 1/2, but they're both going to be negative. So we're going to get a positive root 3. And last, 5 pi over 3. It's going to be root 3 over 2, 1/2. Sine's going to be negative, cosine is going to be positive, so it's going to be negative root 3. So the tangent lines, there's 4 times it goes to the pole, but they overlap each other. They all have the same xy coordinates. 2 of them have the same slope. 2 of them have the same slope. So one of them is root 3x, and then the other one is negative root 3x. But we took advantage of a shortcut here. Otherwise, you'd have to do it this way, which would be a lot more work. And maybe on a problem like this where you're doing 4 points, that would be even crazier. But otherwise, because if you do dy dx, I mean, I could just write it down right here. This is what you would have to plug all these into instead of tangent theta. So dy dx would be the derivative of this on the top. So that would be 1 plus 2 cosine 2 theta. The derivative sine is cosine plus sine times negative 4 sine 2 theta. And then the bottom would be dx d theta, so that'd be 1 plus 2 cosine 2 theta times derivative of cosine is negative sine plus cosine theta times that. The derivative of this would be negative 4 sine 2 theta. So you would have to use this and plug pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3 into this. But the thing that happens here is that the radius, 1 plus 2 cosine theta, this is the radius, right? And since we're at the pole, it's going to be 0, right? And so now you're just left with this term. But then these two parts of it are the same, so they just reduce each other out. And now you're left with sine over cosine, which is tangent. So that's where that shortcut comes from. But if you don't remember it, you can write it back out. You can maybe try and rethink it. Okay, find the area of the region enclosed by this graph. So this is a rose curve with 3 petals and radius of 2. Now, I don't really think we need to sketch this to find the area. Well, it says from on 0 to pi. I think we could just integrate it 0 to pi. I mean, you could go ahead and you could sketch it. 0 to pi, by the way, would be the whole rose curve because it's an odd petaled one. The second set of petals ends up right on top. If you did 0 to 2 pi, that you need to do 0 to 2 pi for an even numbered rose curve. The odd number, you just do 0 to pi, so you get the area doubled. So, I mean, we could just jump right into the area. The area, you should memorize, is 1/2 r squared d theta. And so we're going to do 1/2 0 to pi 2 cosine 5 theta squared d theta. So that's just your setup. And the 2 gets squared, becomes a 4. So now we have 2, 0 to pi of cosine squared 5 theta. And we need to use some trig identities, double angle for cosine, to deal with sine squared and cosine squared. So the identity says, okay, it's going to be 1/2 and 1/2 cosine double angle. And this is true for if it were sine squared or cosine squared. The only difference for sine squared and cosine squared is this is going to be plus for cosine and negative for sine. Okay? Now, I'm going to probably just go ahead and bring this 2 back in. I don't know. I mean, maybe that might help. So the antiderivative is going to be theta plus, this is going to be, so these 2's are going to cancel. So this is going to be sine of 10 theta, but then an extra 10 is going to pop out, so we need a 1/10 here. And so we plug in pi. Sine of 10 pi is 0. And we plug in 0, and sine of 0 is 0. And so the answer ends up just being pi. Alternatively, you could find 1 petal and multiply by 5, but I think that's a lot more complicated because then you have to figure out where the petals end and begin. And I think it's just easier to just, and if they ask for 1 petal, I'd find the whole area and just divide it by 5. That'd be the way to go there. So, okay, find the area of the shaded regions. So I guess the combination of all of them. So I guess I'm just going to find each one on its own. R equals 1 is the circle. So this is the circle, and this is the cardioid. And let's see, both theta equals 0 here. You want to kind of figure out where they start. Theta equals 0 here. It goes this direction. Or I could plug in pi over 2. You get 2, right? So this is pi over 2 for both of them. This is pi for both of them. This is 3 pi over 2 for both of them. So now this area right here, if you want, you could just say, hey, that's a quarter of a circle. That's a quarter of pi r squared. And the radius is 1. So that's just pi over 4. Or you could integrate it. You get the same answer. Treat it like a polar curve. And that's what this one is too. In fact, you know what? If I put this up here, I don't even have to worry about it and just do this whole chunk right here. Find that whole area, 1/2 from 0 to pi over 2 of 2 plus 2 cosine theta squared. And so now when you multiply this out, it's going to be 4 plus 8 cosine theta plus 4 cosine squared theta. There should be a 4 there. We could bring the 1/2 in. And this would be 2. This would be 4. This would be 2. But we need to use a trig identity here, so it's going to be 1/2 plus 1/2 cosine double angle. Bring 2 in. So the antiderivative is going to be 3 theta. There's a 2 and a 1 here. 3 theta plus 4 sine theta plus sine of 2 theta. It's going to give an extra 2 that we don't want, so you need a 1/2 here. And so we're going to get 3 pi over 2 plus 4 times 4. Sine of pi is 0. Plug 0 and you get 0, 0, 0. So we get 3 pi over 2 plus 4. Now, that's both of these regions together. Make sure we did that right. Okay, yeah. Now we got to find this one. This one, we got to find the intersection here, and we got to integrate from here to here, and then do the outer one, and then subtract this inner one. So we got to find the intersection between the two curves. So I'm going to write that up here, intersection. And you would set the radius of one equal to the other. And then you would solve. And alpha equals pi over 3, quadrants 2 and 3, which kind of makes sense. We have another intersection here, right? Quadrant 2 and quadrant 3. I think we want the quadrant 2 intersection. So theta equals 2 pi over 3 plus 2 pi k, and theta equals 4 pi over 3 plus 2 pi k. So theta equals 2 pi over 3 and 4 pi over 3. But this is when we want 2 pi over 3 to pi. So to get that area, we're going to have to say, okay, well, let's find 1/2 of 2 pi over 3 to pi of the larger area. That's the circle. That's the one radius of 1 squared d theta. Now you could try and find that as a fraction circle. You can integrate it like this. I was kind of showing you earlier. You could just do it as like a quarter of the circle. Well, this one is going to end up being a sixth, I think, of the circle. Minus 1/2 2 pi over 3 to pi of the other one, which was 2 plus 2 cosine theta squared d theta. So this is the setup. And now we just got to figure it out. So this is going to be 1/2 theta which is going to be pi over 2 minus pi over 3. Plug that in, right? Which is going to be 3 pi over 6 minus 2 pi over 6 is going to be pi over 6. I told you, it's going to be a sixth of the area. Minus this one, we have to do all that work we did before. I'm just going to skip that and write it down. We had 3 plus 4 cosine theta plus cosine 2 theta. Once we did all this work, right? It's the same thing. The antiderivative is 3 theta plus 4 sine theta plus sine 2 theta, the 1/2 in front. And the 1/2, by the way, is gone at this point because we'd already taken care of that. And it's going to be 2 pi over 3 to pi. And so now if we plug limits in, it's going to be 3 pi plus 4 times sine pi is 0, plus 1/2 sine of 2 pi is 0. We get to subtract all of this, so just be careful. Use some parentheses. That's going to be 2 pi plus 4 times sine of 2 pi over 3 is going to be root 3 over 2, plus 1/2 sine of 4 pi over 3 is going to be negative root 3 over 2. Right? It's getting a little messy. So minus, this is going to be pi, and this is going to be, let's see, maybe we give these guys the least common denominator. So this is going to be 8 root 3 over 4 minus root 3 over 4 is 7 root 3 over 4. 8 root 3 minus root 3, right? And so it's going to be negative 5 pi over 6 plus 7 root 3 over 4. Now, this should be positive. So that's that other area. So we need to add these two areas together. And if we do that, we could give this guy a least common denominator of 6 to go with this guy. So it'd be 3 and 3. So it'd be 9 pi over 6 minus 5 pi over 6 would be 4 pi over 6 plus 4 plus 7 root 3 over 4. And I don't know. I guess maybe I don't know. Maybe we're supposed to find each one individually. Maybe that's the way I originally designed it. But this would be the total combined area. If you were to find them all together. Individually, this is that chunk. This chunk minus pi over 4 would give you that other region right there. So that would be 6 minus 1, 5 pi over 4 plus 4. That would be that region. And this would be that other region there. So those are the 4 different separate areas. But altogether, this is what they would add up to, if I did that correct. So there you go, some good practice. Obviously, study your original test and any other review assignments leading up to your original test, pre-tests. Practice the kinds of problems that you had trouble with. I guess on problem 12, I should have done a sketch to figure out where the tangent line would be. Real quick, this is what the sketch would look like. It's a limacon with an inner loop, and that's why we get 4 tangent lines, so just 2 or something. And regular limacon would just have a horizontal, tangent here. You wouldn't get these slanted ones. So that's it. Get ready for your retest.